Hello everyone. In this lecture, we're going to focus on the importance of quality in lean production, discussing reducing and preventing defects. The learning objectives are to review the role of quality in lean production and to look again at the Six Sigma methodology for defect reduction. We want to understand the reasons for early detection and prevention of defects and define automation and explain its role in lean production. And finally, we want to understand how providing immediate feedback is enabled by employee empowerment, in particular, the and-on pull. So at the beginning of this course, we discussed how lean production tools are used to reduce the three M's: Mura, inconsistencies; Muri, overburden; and Muda, waste. And we discussed how the objective of these lean tools is to create continuous flow in our processes, increase the flexibility to match customer demand, and to eliminate waste through quality and quantity control. We've learned to establish continuous flow in the face of setup times and variability, and we've used pull scheduling techniques to achieve just-in-time production. And all of these are geared then towards quantity control. In this lecture, we will look more closely at quality control and how this affects our process. And we'll start by going back to our 7 wastes of lean: transportation, inventory, motion, waiting, overprocessing, overproduction, and defects. And thus far, we've looked primarily at our production in order to reduce inventory and waiting. Now we will look more closely at our last waste, defects. Again, defects means producing product that does not meet specifications. Causes can be the methods we're using, the materials, the equipment, the operators, the environment. How can we reduce this? Well, we can improve process capability by analyzing our process and solving for the root causes of the defects. And without recapping the topics of the first 2 courses, we know that Six Sigma does exactly this. Six Sigma tackles defect reduction by identifying the critical to quality output parameters, which we called Y, and identifying the factors that influence or affect these critical to quality parameters. We call these the X influencers. And then, following our DMAIC cycle, define, measure, analyze, improve, and control, we would measure the variability of our critical to quality parameters. And this was represented by Six Sigma, 6 standard deviations of that normally distributed parameter. We would see how this compared to the allowed specifications, the lower and upper spec limits defined by the customer. And then, through analyzing the data and running experiments to improve the process, we would reduce the variability so that we would have a much more tightly controlled process, improving the capability of the process and reducing the number of defects. Defined by Motorola, a process achieving 3.4 parts per million defects has a Six Sigma capability. And then finally, as part of the Six Sigma methodology, we would control and monitor our process. Now, why was this Six Sigma capability so important? Well, we also learned about process yield, and we saw that a complex process with many steps can have unacceptably low yields, even for fairly high yields at each individual step. And for a product with like a car with thousands of parts and processes, the Six Sigma capability is required even to achieve a reasonable final yield. We saw this again in this course in the overall equipment efficiency lecture, so that the yield is measured as part of the OEE, where we look at the availability rate, the performance rate, and here, the quality rate. The quality rate is reduced then to losses due to quality issues, rework and scrap due to defects. And we also understood the effect of defects not only as a loss of this production yield, as this quality rate, but also as a loss of resources in our production: materials, labor, and capacity. And the cost of these internal failures include the cost of scrap and rework and delay of deliveries. Defects can also lead to external failure costs, when the defective parts reach the customer. This can cause possible recall, warranty costs, also well as reputation loss. Now, defects are not easy to detect. They're often very hard to measure when they're very rare and have many different root causes. But already we can see that early detection is better than late detection. Now, why? If a problem is detected early, the number of defects can be reduced and the internal failure costs can be reduced. Now, here we want to see how this works when we compare a push and a pull system. Now remember, in a push system, inventory is allowed to collect between the steps. So for example, if step 1 is producing good parts, but the inventory is allowed to build up between step 1 and step 2. It continues to process its good parts, and then it has a problem. Step 1 has a problem, and it produces a defective part. Now, in the best case, you'll detect this defect at step 2. But because there's so much inventory built up between step 1 and step 2, all of these good parts have to be processed before the defective part will move to step 2 and the defect will be detected. So time is going by. And while this time is going by, step 1, what is it doing? Well, it's got a problem. No one knows about the problem. So it is busy filling up this inventory buffer with defective parts, which then also have to be flushed out through the system. Now, in contrast, in a pull system, where the inventory is limited, and we saw, of course, the example with Kanban cards, but you have limited inventory between the steps. If you have an activity producing, and then it starts to produce a defect, the time till the detection will depend on the amount of inventory between the steps. And since this is limited in a pull system, the detection will occur much faster. So again, pull systems limit the inventory and thus the time till detection. And as we said earlier, if a problem is detected early, then the cause can be identified early. Why? Because as we saw in course 2, when you're doing your cause and effect analysis, for example, your fishbone diagram, the inputs to your cause and effect analysis are limited to those processes preceding that detection. And so if it's identified more quickly, you can more quickly see what went wrong in those processes at almost the time that the defect has occurred. But of course, prevention is better than inspection. Why is that? Well, inspection is adding non-value-added costs and capital for that inspection step, and it doesn't remove the cost of scrap or rework. An inspection is never perfect. Defects can slip through and cause external failures. And very importantly, inspection removes the responsibility, because the inspection is not, to find the defect, is not occurring where the defect occurs. It's downstream from where the actual problem is. And inspection itself can become a bottleneck in your system. Better is prevention, quality at the source. And prevention typically costs less than the combination of inspection, internal and external failure costs. Now, how can we achieve this? One of the most well-known tools of lean production are the built-in tests that signal problems automatically and immediately. And this brings us to the topic of automation. As we said in the first session, Toyota Motor Corporation grew out of Toyota Automatic Loom Works, founded by Sakichi Toyoda. And as we said, a particular feature of the looms was that they would stop automatically as soon as a thread broke. In other words, a defect would stop the production immediately. And this affected the principle of jidoka, or quality at the source. And this was described by Taiichi Ohno as automation, or automation with a human touch, and meant that a machine could distinguish between normal and abnormal operating conditions. If something went wrong, the machine would stop immediately and no defects would be produced. And this emphasizes the idea of waste. With no extra inventory to hide the problem would be visible, and this allows immediate improvement of the process. Now, just a note, this is very different than our Six Sigma idea of improving variation. Here that we see in lean production, no defects are even produced. Now, we've already covered other tools and methods used in lean production and Six Sigma to prevent defects. For example, total production maintenance enables preventive maintenance. This then helps prevent defects due to equipment malfunction or breakdown. We looked also at 5S and workplace visualization, which helped to standardize the workplace, organize the workplace, so there's less room for misprocessing. We also learned about statistic process control, where in the Six Sigma methodology, you have a control and monitoring method with a response plan in case of any deviations from a stable process. Another important tool in lean production is Poka-Yoke, or mistake proofing, any mechanism that helps to avoid making mistakes. And here are just some quick examples. For example, the SIM card has a cutoff corner so that you don't put it into your mobile phone incorrectly, or you have connectors that are designed that the connection cannot be made incorrectly. A less high-tech example is, for example, padlock. So good padlocks don't release the key if they're not totally locked. And here we also only want to briefly mention the critical concept in lean production of employee empowerment. In the context of preventing defects, we want to emphasize the importance of responsibility of the operator in production. In particular, the idea that in order to promote a culture of identifying and responding immediately to defects, the operators have the authority to stop the line if a defect is detected. And this comes again to the idea of jidoka, or quality at the source. And as we spoke about in workplace visualization, in the displaying status, the famous Andon pull is one example of displaying the status of a line. And it also, though, illustrates how employee empowerment is a strong component of preventing defects and enables a systematic, continuous improvement of the production. Team members are encouraged to pull the andon cord whenever there's a problem. The production line will then stop, and the team leader is then alerted by lights or sound to assist the team member who has the problem. And in this way, every problem is addressed immediately instead of continuing to produce out-of-spec products. So we've reviewed here in this lecture the impact of defects on our process, and we've understood the target should be in lean to prevent defects from occurring. Now we want to look again at the impact of defects can have on our production flow.